Well, good morning to you. The good news is that there's only, I think, counting today, 4 more times that you have to get up and be here at 8 a.m., so that's good. The bad news is there's a final at the end of all of this. So what I want to do today is practice solving NMR spectra. I also want to tell you a little bit about carbon-13 NMR. Carbon-13 NMR is very useful for organic chemists. It's a little bit more difficult to interpret, and your text doesn't emphasize it a lot. So I need to introduce it to you without going too far down the rabbit hole. Before we do that, since we've gotten to the point where we're solving NMR spectra, I want to just do one more unknown. And your strategy in solving the structure of an unknown should be to use all the information available to you. And just like when you're playing a Sudoku puzzle, I don't know if any of you ever done that. You're not retirees, so I know you're not carrying around little printed Sudoku booklets. But if you had ever done that, you would see that for some cells that you're trying to solve the numbers, you can get the answer from multiple sources. There's multiply reinforcing information. And for other spots, there will be only one way to get the desired information. Same thing can be true for an NMR unknown problem. You will often have multiple sources of information that reinforce that the correct structure is indeed correct. So let's go through that. The place I start with a problem like this is I start by wanting to know how many pi bonds or rings are in this molecule. That's a highly useful piece of information. So if this is the molecular formula, I can use the equation that I gave you to calculate degrees of unsaturation or double bond equivalence. Or I could, if I had a calculator, I'm good in my head. Let's see, 2 times 3 is 6 plus 2 is 8, minus 8 is 0. There are no pi bonds or rings. Okay? Notice actually how the rest of the data confirm that observation. For example, in the IR information, I have a large, broad, and strong peak at 3,600 inverse centimeters to 3,200 inverse centimeters. Notably, I don't have a peak at 1,600 to 1,750 or so, which is where you would expect a carbonyl to be. So sometimes the absence of evidence is also evidence. And in this case, we can't have a pi bond or a ring. We don't see a carbonyl. That checks out. Another thing we don't see is absorbances in the region that would, we don't see any NMR signals in the region that would correspond to like alkene protons. So that checks out. No double bond equivalence. However, in terms of functional groups from the IR, what peak shows up in this range of wave number but is strong and broad? The OH peak. Now you'll have a table. Some of you like to know ahead of time what the table is going to look like. It is posted on the content page of Learning Suite as a PDF under the heading pKa, A-value, NMR table, or whatnot. That will show you exactly what will be available to you on the back of the exam as you take the exam. All right, so another key piece of information, this molecule is an alcohol. We have an OH group. How do I know it's an alcohol and not a carboxylic acid, which also has an OH group? There's no carbonyl. Okay? So with that in mind, let's now turn to the NMR spectrum, because all I know now is that I have an alcohol, it's got 3 carbons and no double bonds. There's maybe a few. If we want to, we can sketch out some possibilities. A 3-carbon alcohol, that's a 2-carbon alcohol. Let's erase that. A 3-carbon alcohol, let's see, we could have that one, or we could have this one. Can you think of any other 3-carbon alcohols? Okay, so we've already almost solved the problem here. Let's look at the connectivity. Let's look at the information we can get out of the NMR spectrum. Remember, we've got number of signals, we've got chemical shift, we've got peak area, and we've got spin-spin splitting. So first, I see 3 NMR signals, 3 different kinds of protons. that may be enough to tell me which one of these it is. How many different kinds of protons are present in my 1-propanol alcohol? Four. The OH proton is 1. These two CH2s are enantiotopic. They're identical. These two CH2s are enantiotopic. They're identical. And these methyl protons are homotopic. They're identical. So, if it were this 1-propanol, I would expect 4 NMR signals. Is that consistent with the data? No. Okay, so I can probably rule that one out. Now, before we go selecting B or whatever and moving on with our lives, it's good to check your answer to make sure it is in fact consistent with the data. So, looking at this 2-propanol or isopropyl alcohol, how many NMR signals would we expect? 3, right? Because I've got 1 there, the OH proton, 2, the CH proton, and then I have 2 methyl groups. Those methyl groups are enantiotopic, so they're identical. So I would expect to see 3 NMR signals, a 1-proton signal for the alcohol, a 1-proton signal for the CH group, and then a 6-proton signal for the methyls. Okay? Let's check out the spectrum. Indeed, 1, 1, 6. So that checks out. Integrated peak area checks out. Now, we could say we're done, we've solved it, but it's actually a really good idea, even when you think you know the answer, to just make sure your answer actually is consistent with all of the data. So let's now see if our answer is consistent with chemical shift. We've got 1 proton with a chemical shift of around 4. We've got 1 proton with a chemical shift of around 2.5, and then we've got 6 protons with a chemical shift of 1.2-ish, all right? Maybe useful also to look at peak splitting at the same time. The 6-proton NMR signal is a doublet. The 1-proton NMR signal is a 1, 2, 3, 4, 5, 6, 7-line pattern, septet. A doublet is what we would expect for 6 protons that have 1 adjacent proton and only 1 adjacent proton. A septet is what we would expect for a proton that has 6 identical adjacent protons. And so that's consistent with our data, right? Our pink proton is adjacent to the 6 methyl protons. Our methyl protons are adjacent to the 1 pink proton. Oh, by the way, the pink proton is actually adjacent to the OH group. Why isn't it split by the OH group? Because OHs are weird. Right. OHs are weird. In most cases, hydrogen bonding and rapid proton exchange between molecules prevent the nearby proton from seeing the 2 different spin states possible for the OH group. Lastly, we do see a proton that is a singlet. It's not split by anything else. That's consistent with the fact that the pink proton is not split by the OH proton. In terms of the chemical shift of the alcohol, we got nothing. It can appear basically in a lot of places from around 1 to 5 ppm, so we're not really getting any information from its chemical shift. In fact, we sort of settle on the fact that this is an alcohol peak by process of elimination. Okay. So we've looked at chemical shift, we've looked at integrated peak area, we've looked at splitting, we've looked at number of signals. All of that points to the fact that this is our unknown molecule. All right. So we were able to settle in on an answer pretty quickly, but it's better, instead of just moving on and forging ahead, to make sure all of the data are consistent with your answer. Okay. Other questions? So before we do some more unknowns, let's actually talk about C13 NMR. So as I mentioned at the beginning of this spectroscopy C section, some nuclei have magnetic moments, and you can learn about which nuclei have magnetic moments if you want to delve into nuclear shell theory, which I think is mostly none of you. But if you wanted to, there are reasons why nuclei have magnetic moments. It has to do with the number of protons versus neutrons. C13 happens to be a nucleus that is NMR active, that is, it has a magnetic moment. However, C13, unlike proton, unlike hydrogen, which is like 98% abundant, C13 is only 1% abundant. The dominant isotope for carbon is carbon-12, and carbon-12 is not NMR active. So whereas for proton NMR, every proton in the molecule was basically NMR active, for C13 NMR, only 1 out of 100 carbons are going to be NMR active. Now that's okay because a mole is a really large number of atoms, right? 1 out of 100 of 6 times 10 to the 23 atoms is still 6 times 10 to the 21 atoms, which is still an enormous amount of atoms. What I'm saying is that in a sample of an organic molecule, probability tells us that in that sample, we're going to have C13 at pretty much every one of the carbons in a molecule, just not all in the same molecule. So for our isopropanol, for example, one molecule would have a C13 here, and another molecule would have a C13 there, and another molecule would have a C13 there. And so on average, if we take an organic molecule and try to take an NMR spectrum and look for carbon, we will see it. But because the odds of having 2 carbons adjacent to each other in the same molecule, being C13, are now only 1 out of, probability 10,000. We don't see that very often. And so there's no actual, we don't see any carbon-carbon splitting like we do for proton-proton splitting. So for a carbon NMR spectrum, mostly what we get is individual singlets for each carbon in a molecule. There can be carbon-hydrogen splitting, that does happen, but there's a cute experimental technique we use to turn it off because it actually makes the spectra complicated and difficult to interpret. So shown here, the biggest thing we're going to get out of a C13 spectrum is number of different carbons, and then we'll get chemical shift information. Different kinds of carbons in different environments have different chemical shifts. Go ahead.
And so your carbon-13 spectrum is completely different from your hydrogen spectrum. They don't interact with each other?
Right. The carbon spectrum and the hydrogens don't interact with each other. They are decoupled. They totally do interact with each other. You can just turn that coupling off. Yeah. A couple other things to know, because C13 is so low in natural abundance, the signal to noise ratio for a carbon-13 spectrum is a lot lower. What do I mean by signal to noise? That's an analytical chemistry term which you may not have heard, but signal to noise refers to how well can you tell when you're actually seeing a proton or a carbon versus when you're just seeing nothing. Notice that for a proton spectrum, the noise looks like a straight line. Now it isn't. If you zoomed in close enough, you would see and you still can't even see it if we zoom in, you would see that that line is wiggling around. But the signal is so much larger than the noise that it's very easy to tell when you're seeing a proton versus when you're seeing nothing. Now look at this C13 NMR spectrum. Do you see that the baseline there is wiggly? That's what nothing looks like, but the signal to noise is a lot lower. These peaks do rise out of the noise, but not as far. That's generally not a huge problem for C13, but if you wonder why the baseline there is so wiggly, it has to do with the natural abundance of carbon and some other things that we won't worry about. But in general, C13 is not as sensitive an experiment as an NMR, as a proton NMR experiment. you go downstairs in our NMR facility here and take a carbon NMR, often you need to run the experiment for longer in order to see a spectrum versus a proton spectrum you can often run just in a few minutes. Okay, so here's a C13 spectrum of acetic acid. There are two different kinds of carbon in acetic acid. There is the carbonyl carbon and then the methyl carbon. And chemical shift, so NMR, you should expect to see two different peaks in the C13 spectrum, and we do. You'll also notice that the chemical shift varies much more over a much broader range of values for carbon than it did for proton. So for carbon, we're looking from 0 to 200 or 220 ppm, whereas for proton, we were looking just from sort of 0 to 12 or 0 to 15. Much of what we learned, everything we learned actually about identifying different kinds of protons applies to identifying different kinds of carbons. So if you can interchange carbons by rotation around a bond or by some symmetry operation, the carbons will be identical. Everything we learned about homotopic and antiotopic and diastereotopic applies to carbons. In terms of chemical shift, generally the same principles for shielding and de-shielding apply. That is, being adjacent to an electronegative atom causes you to be at higher chemical shift. I'm just going to show you, one other thing. Importantly, peak intensity or peak area for C13, for some reason that I don't know, is not actually proportional to number of carbons represented by a peak. So you can't actually look at peak height or integrated peak area for a C13 spectrum and say, oh, I know how many carbons are in that peak. For example, it would be incorrect here to say there are more carbons represented by this peak than there are represented by this peak. They're each just one carbon. So you sort of have to turn off that intuition that you developed from proton NMR. I want to show you some C13 chemical shifts. I won't provide a table like this on the exam because, frankly, you won't need it. But it's available in the text, and there will be some problems I think you do in the study guide that'll have you just do some basic interpretation of C13 data. So, as you'd expect, carbons that are just alkyl groups show up in the shielded region of the spectrum. You add an electronegative atom like nitrogen, oxygen, or a halide, you de-shield somewhat. Being attached to an alkyne, being in an alkyne triple bond actually moves you into the 60s to 100s part of the spectrum. Being in an alkene moves you in the 100s to 140. Being attached to benzene moves you to 120 to 150, and then being a carbonyl moves you in the 160s to 210s. So that's sort of the general pattern that you're looking for. Here are some example C13 spectra. Here is one propanol, and you can see that the carbon that is closest to the OH group is most de-shielded in chemical shift, and then basically the chemical shift tracks with proximity or distance to the OH group. So the B carbons show up here, the C carbons, the methyl groups show up here. You should not try to interpret the difference in peak height here. I have no idea why the C proton is lower in intensity than the A proton. There actually is an explanation for it, I just don't know it. It's nice to know when you can care about something versus not care about something, and that's something that you can for sure not care about. Unless you want to, in which case go ask somebody, but not me, because I don't know. Okay, here is an ester. Again, 3 different carbons. You expect to see 3 different peaks. Again, chemical shift tracks with proximity to electronegative atoms. The carbon that is attached to the carbonyl oxygen is the most de-shielded. Next is the carbon directly attached to this ester oxygen, and then next is the methyl group. Okay, so this is about as difficult a problem as you could anticipate for C13 and 351. Let's identify the different kinds of carbons and the different peaks. So how many different kinds of carbons does this molecule have? 3. You got the carbonyl, you got the 2 CH2s, which are homotopic, exchangeable by rotation around an axis that coincides with the carbon-oxygen bond, and then you have the methyls. Okay, so which peak is the carbonyl? Or the carbonyl carbon? The most de-shielded one, okay? Next, that one, and then the methyls should be here. Easy enough? Okay. You would never try to solve the spectrum of a molecule or solve the structure of a molecule from the NMR spectrum, the C13 NMR spectrum alone. You just wouldn't do that. That would be silly. It's actually much easier to get proton NMR data. You will sometimes use the carbon spectrum to confirm that your proposed structure is correct, because your proposed structure then can tell you how many different kinds of carbons that you have. Okay. Well, with that, let's now practice. I've got like a ton of these, so let's go. We'll do one together, and then we'll sort of turn you guys loose to have you come up with some ideas while I sit here at the front and just stare at you. So, okay, formula C4H8O2. Go ahead and calculate the number of degrees of unsaturation or double bond equivalents that must be in that molecule. I don't want to commit to it. I'm afraid I get the arithmetic wrong. What have you got? 7? 1. Okay, good. 1. All right. And the IR, what kind of functional group does the IR tell you you have? Yeah, that strong peak at around 1750 inverse centimeters is consistent with a carbon-oxygen double bond. Importantly, the IR doesn't show you an OH group. Your formula says you got 2 oxygens. Whatever that other oxygen is, it's not an alcohol. That's going to limit the number of possibilities we can draw here. Okay, so we can already sort of put together some proposed pieces for this molecule. We know that we're going to have a carbonyl carbon bonded to 2 things, and somewhere else in the molecule we're going to have an oxygen bonded to 2 things. We don't yet necessarily know whether this oxygen is attached to the carbonyl carbon or whether there's something else going on here. For that, we're going to need connectivity, and for that we'll turn to the NMR spectrum. So I find it sometimes useful to list the peaks, their chemical shifts, how many protons and how many protons they represent in a little table. Let's deal with, I see 3 different kinds of peaks, so 3 different kinds of protons, 3 different NMR signals. Let's deal with integrated peak area. For once, you're given a spectrum here where they don't tell you the number of protons that are represented by each peak. They show you the area. This little curved line tells you that the machine or the instrument has integrated the area under the peak, and it spits out that number helpfully in arbitrary units that mean nothing, but they're all proportional to each other. So 23, 29, and 30. In interpreting these numbers, you have to relax your eyes a little bit. If you're thinking in 2 significant digits, you're probably thinking too hard. All right, so we're looking for basically relative peak ratios. So tell me, what's the ratio between this peak at 4 ppm and this peak at around 1.9? 2 to 3, okay? Please do not tell me, but Dr. Price, 23 divided by 29 is not 0.666666666. I can't stop six. I'm sorry. Please don't tell me that. I don't care. Right? We're not thinking that hard, right? You're overdoing it if you're thinking at that level. It looks like a 2 to 3 ratio. That's close enough. So that tells me that now I can sort of guess as to how many protons are represented by each peak if I know the total number of protons in the molecule. It just so happens that if this is 2 and this is 3 and this is 3, that adds up to 8. So that's probably a pretty good assumption. So I think the peak at 4 ppm is worth 2 protons. I think the peak at around 1.9 ppm is worth 3. And I think this peak at 1.2 ppm is worth 3 protons. Okay. Also, 29 and 30, for our purposes, one significant figure, same number. Okay. So it may help you to write down, okay, I've got a peak at around 4 ppm. It is worth 2 protons, and then it may help you to write down the splitting. So that one at, what kind of splitting pattern is that at 4 ppm? Yeah, that's a 1 to 3 to 3 to 1 quartet. I'm going to represent that with the letter Q. How about the peak at 2 ppm? That's worth 3 protons. Singlet, okay, and the peak at 1.2 is what? Triplet. Okay. Quartet tells me that the protons represented by that peak are adjacent to how many? 3 adjacent protons, okay? Now, can you think of a structure that involves 2 protons that are adjacent to 3? Yes, CH2, CH3. And the peak, of course, of interest here is the protons, the CH2 protons. Okay. How about the singlet? How many protons are adjacent to it? None. None adjacent protons. That doesn't sound great. Can you think of a structure that has 3 identical protons that are adjacent to no other protons? That's just a methyl group, and whatever's over here, no protons, right? How about the triplet? A 3 proton adjacent to how many? Okay. This is where we're getting complementary information, because just above we drew a structure that accounted for a 2 proton quartet. The triplet peak accounts for those 3 protons that are coupled to 2. Do you see how that's sort of reciprocal information? Okay. So let's see. I'm going to summarize the pieces that we've identified so far. We haven't really considered chemical shift. The 2 protons that are at 4 ppm, what do we think they're next to? We got 2 choices of things you can be next to that don't have protons on them. You can be next to an oxygen, or you can be next to a carbonyl. Being next to an oxygen gives you chemical shift in the 3 to 4 range. Being next to a carbonyl gives you chemical shift in the 1.5 to 2.5 range. So, what do you think the CH2 is next to? Got to be next to the oxygen because of chemical shift. Okay? So, now we can elaborate on our structure a little bit more. Okay. How about the methyl group? We're running out of places to attach things. At this point, the problem starts to solve itself. But the methyl group that's a singlet, what do you think it's attached to? The only other places we have to put stuff actually are the carbonyl. The chemical shift, though, is consistent with being alpha to a carbonyl, right? So at this point, I've accounted for all of the carbons. There are 4, 1, 2, 3, 4. I've accounted for both of the oxygens, 1 and 2, and I've accounted for all 8 of the protons. The only choice I can make at this point is to attach this group to the other position of my carbonyl. So the final structure should be that molecule. Okay? Has to be. Now, it's usually good at this stage to go back and check and make sure that the data are consistent with your hypothesis. We notice that there's a carbonyl, so we are checking that off. We notice there's only 1 double bond equivalent, so we can check that off. There are 3 kinds of protons in this structure. We would predict the methyl protons there adjacent to the carbonyl to show up at around 2 ppm and to be a singlet. We would expect the CH2 protons to be a 2 proton peak, but in the range of 3 to 4 ppm and to be a quartet, and they are. We expect the methyl protons here to be a triplet and to be in a relatively shielded region of the spectrum, and they are. And with that, we can be confident, we enter our answer, we move on. And we laugh because you have foiled the evil person who wrote the problem for you. You've got the answer. Okay, questions about that process? That seemed easy. It was. Okay, now you do this one. Same formula, same IR information, different spectrum. You guys done yet? Now you're.
I don't want to say it, so you keep drawing.
You want to know? Okay, all right. Okay, what have you got? Same formula, right, as last time? And same kinds of pieces? So how are you putting them together? Don't be afraid to be wrong. We promise not to laugh at you. Go ahead.
Basically, oxygen's in between everything.
Oxygen's in between everything. Okay, so how do you know that? Tell me more about that.
Yeah, so they're all singlets, meaning that there can't be any carbon hydrogens next to other carbon hydrogens.
Okay.
So then it has to be methyl coming off the carbonyl, and then another carbon in between the carbonyl and the ester, and the last carbon on the other side of the ester.
Okay, so you're saying that because these are all singlets, but you do know that they're a 2 to 3 to 3 ratio, right? So that means you've got methyls. I mean, and there's not that many ways to have 3 identical protons that are not a methyl group. So, so it's a pretty good assumption that these 2 peaks that are singlets represent methyl groups. The thing you have to do is to, realize because they're singlets, they're not adjacent to anything else. Now, figuring out exactly the way things are is a little bit tricky. What does chemical shift tell you about these 2 protons? Sets of protons, rather. In the range of 3 to 4, that's where we expect protons that are adjacent to oxygen. So that would suggest that at least one possibility is something like this. Okay. And then what else? I guess the only thing I can do now to make everything be a singlet is to have the carbonyl be on the other side of that CH2 group, right? Okay. So now we can check our answer against the data. Methyl group adjacent to a carbonyl, it should be a singlet. We predict somewhere in the range of 1.5 to 2.5 ppm. In fact, that's what we see. Oh, that was punny. That's the appropriate laugh for that joke. Okay. Methyl protons adjacent to an OH group and nothing else. That's what we expect for for the A protons. How about these CH2 protons? Can you think of an explanation for why the orange protons are de-shielded relative to the blue protons? Go ahead, say that. You don't have to say it. Oh, you're muttering it to yourself. Okay, that's good. I will mutter to the group what was being muttered. I'm teasing, sorry. It's between 2 things, right? It's between the oxygen and the carbonyl. The de-shielding impact of being adjacent to oxygens or adjacent to carbonyls is somewhat additive. So these orange protons are de-shielded for to some extent by being adjacent to an oxygen, and then a little bit more by being adjacent to a carbonyl. Okay, this is the right structure. This is all we could do. I didn't color I guess I will have to come back later and color in the walker. That's kind of a crude walker, but oh well. Why is the TIE fighter shooting the walker, though? That's what I want to know. Probably because it's been commandeered by Ezra Bridger and Garazeb Aurelius. There's probably 2 people out there that know what I'm talking about. Okay, let's do this one. This one's a little more difficult. In part because it totally dumps IR information at you without telling you anything about peak intensity. So I don't know what to do with that IR information. I would basically ignore it. Probably they should have shown you a spectrum. Start with the formula. Go ahead and calculate double bond equivalence there and or degrees of unsaturation, and I will give you a hint about structure based on the number you calculate there. Remember that when we calculate double bond equivalence, we add the number of nitrogens and subtract the number of halides. That has to do with the number of things that nitrogen can be attached to. So what have you got? 4. Good. Anytime you have 4 degrees of unsaturation or double bond equivalence in a relatively small organic molecule, a really great way you can take care of 4 double bond equivalents without using that many carbons is a benzene ring. Notice a benzene ring has 3 pi bonds and a ring, so that takes care of your 4 double bond equivalents right there. So already, if it were me, if I see 4 double bond equivalents, I'm already hypothesizing benzene ring. And if I look at the NMR spectrum, I see a cluster of peaks representing 5 protons, and it's in the region of the spectrum that is consistent with aryl protons, that is protons attached to benzene rings. So I'll go ahead and write this as part of our structure. It's a mono-substituted benzene ring, and I told you previously last time that you can analyze this. Technically, the mono-substituted benzene ring should have 3 different kinds of protons. Sometimes the way the peaks appear and their splitting pattern can be different depending on what this group is that's attached to the benzene ring. We said we wouldn't interpret that in any level of detail, so for now, just looking at this 5 proton peak, knowing that it shows up in the region of the spectrum that's consistent with aromatic protons or protons attached to benzene rings is enough. Okay, any questions about how I got to that conclusion? Okay, let's do the rest of it. And here you're lucky because 2 protons, 2 protons, 2 protons. If I'm following along with the molecular formula, I've already accounted for 6 carbons and 5 protons. So I need 2 more carbons and I need 6 more protons. All right, what do you think about this 2 proton triplet? What is it next to? It would need to be next to another CH2 group, right? And this 2 proton triplet would also need to be next to another CH2 group, where what's on either side, whatever it is not a proton. So if I'm checking things off, let's see, we've dealt with 2 of the remaining carbons. We've dealt with 4 of the remaining protons, so now we need to deal with a nitrogen and 2 protons. I've got this 2 proton singlet here. What do you think that is?
NH2.
Possibly an NH2. If they had given you the full IR spectrum, these 2 peaks probably correspond to stretches of the NH bond. Probably they're very weak and they're somewhat broad. Again, they probably should have shown you the IR spectrum there. So with that, I can pretty well piece together the molecule. I have the mono-substituted benzene ring. I have a CH2 group here. a CH2 group there, and then an NH2 group. I'm not surprised that the NH2 protons are not split, because hydrogen bonding and rapid proton exchange makes it so that the adjacent protons don't feel the magnetic field influence of those NH2 protons. I'm also, so I shouldn't be worried that these protons adjacent to the NH2 group are not split by it. Okay, so it's pretty clear that we've got it. Let's deal with the issue of which of the CH2 groups are B or C. Which do you think is more de-shielding, being near a nitrogen or being near a benzene ring? I don't know, actually. I don't know what the answer is. It's difficult to say. If we look back at our NMR table and look at what to expect, we can see that being adjacent to a heteroatom, nitrogen, oxygen, halide, can have us in the 2.5 to 4 ppm region, whereas being adjacent to a pi bond, and this would include being adjacent to a benzene ring, should be in the 1 to 2. Now, I'm not talking about protons that are directly attached to a benzene ring. That's in the 6 to 8 region, but being adjacent, being on a carbon that is adjacent to a benzene ring would also put you in the 1 to 2.5 region of the spectrum. So there's a little bit of overlap there, right? And that's probably why. I'm going to sneeze here. Actually, I guess I'm not. That's annoying. Ever done that? Needed to sneeze but couldn't. That's why if I were guessing, I would guess that the protons adjacent to the nitrogen are probably these ones at higher chemical shift. Being adjacent to the benzene ring puts you in the range of 2 to 2.5 ppm. So that's sort of how I would assign things. But in this case, you don't actually need to know that as long as you don't actually, the precise issue of whether the peak at 3 corresponds to the B protons or the C protons maybe doesn't matter so much as having the correct structure. Okay. So all of these problems can be found in your text, and you should practice. The only way to do this is to do just do a ton of these on your own so that you get comfortable solving the spectra. I've lifted all of these spectra directly out of your text, and so go to the end of the spectroscopy chapter and just start doing problems. With that, let me tell you a brief story in the last couple of minutes. I sometimes tell this story this time in the semester when you're getting stressed out. What time is that in the semester? Well, it's the whole semester. I took this class, 351, in the fall of 2000. At that point, I was newly back from a mission, and I was dating a girl named Amber Allen, who's now Amber Price. So you know the way the story ends. But the way I kind of studied a lot, and I would sort of study as hard as I could until like 9 or 9:30. I was also went to bed early. I was newly back from the mission. You still have old habits. I didn't stay up that late. Anyway, so I'd run over to her apartment, and her apartment was nicer than mine. I lived in a dump. I won't tell you which place it is, but it still exists. I drive past it occasionally and shudder. Anyway, I would walk down to her apartment. We'd talk for a minute. I'd kiss her goodnight and then run back to my apartment, study a little bit more, and then go to sleep. And the 2 minutes a day I was giving her was really not enough. And I can still remember driving down University Parkway on a date, and she wasn't happy, and I kind of thought, are we breaking up? And she asked me the question, don't you want to spend more time with me? And the only thing that came to mind was, well, on Wednesdays I could, which, as you know, is the wrong answer, right? I was sort of prioritizing what I thought was perfection in my studies versus actual human relationships. It worked out. I adjusted, actually. I just started studying at her place, and then being in the same place as her actually counted as spending time with her, which doesn't sound any better, does it? It turns out over time I've had to realize that people and relationships are more important than assignments and perfection. That's been a long, hard lesson. It's taken me maybe 20 years to get there. I hope it won't take you 20 years to get there. The things you're going to take forward into the next life, in addition to the light and knowledge you gain in this class, will be your relationships. So please make sure, I'm talking out of both sides of my mouth because I'm the problem here, right? I'm the one giving you all this stuff to do that's stressing you out. Please take time for other people around you. Your lives will be happier. All right, get out of here. We'll see you Friday.